Have you ever looked up at the night sky and, well, truly wondered how far we've actually reached? It's kind of incredible to think about humanity's journey, right? From just staring up at the stars to, actually stepping foot on another world. Today on the deep dive, we're going to challenge some common ideas about our cosmic neighborhood. Like, what do you think our closest cosmic neighbors really are? Okay, let's unpack this. Our sources for this deep dive, they show some really fascinating things about how far we've gone, where we're aiming next, and maybe even some totally unexpected places we might eventually call home. It's quite a trip.
It really is, and that's why having good sources is so important here. Space is just so vast, and the challenges, well, they're enormous. It's hard to even get your head around it without solid information. So these sources, they bring a lot of clarity, which is invaluable.
Absolutely. So let's start right here, our immediate cosmic neighborhood. When you think of the planet closest to Earth, what pops into your head? I mean, for most people, it's Mars, isn't it? All the talk about missions, colonization.
That's the common thought, definitely. But the data, when you average it out over time, it paints a different picture. On average, the closest planet to us isn't Mars, it's actually Venus.
Venus. Wow, okay, so about 41 million kilometers away on average.
That's right, around 41 million kilometers.
And Mars, the place we're actively planning to send people, is further out, like 78 million kilometers average.
Yep, around 78 million. So Mars is the most realistic travel target for humans right now, even though it's not technically the closest on average.
And what about Mercury? I guess it's just too close to the sun, right? Too hot, too dangerous.
Exactly. Mercury is about 91 million kilometer average distance, but the solar radiation and heat make it incredibly challenging for human travel. And the gas giants, Jupiter, Saturn, they're way out there, hundreds of millions, even billions of kilometers, visited only by robots like Cassini or Voyager.
Right, so that dynamic distance thing you mentioned, how does that play into planning missions?
Well, what's fascinating here is how these orbits constantly shift the distances. Closest is always changing, moment to moment, but that average distance is key for planning. It affects, how long the trip takes, when you can launch, the fuel needed. It really shows that just being close isn't the whole story. The planet itself matters hugely.
Okay, so speaking of journeys, how far have humans actually gone? With our own feet. Most of the time, we've had people in low Earth orbit, LEO. That's, only about 400 kilometers up. The ISS, the International Space Station, has had people on it continuously since the year 2000, living and working up there. But the absolute furthest, that's still the moon, right? Around 384,400 kilometers away.
That's correct. The moon. 12 NASA astronauts, the Apollo missions between 1969 and 1972. That's it.
And it's so important to remember that. All the other amazing missions, the Mars rovers sending back pictures since '97, probes flying past Jupiter or Saturn, those have all been robotic. No people involved beyond the moon.
And this raises a really interesting question, doesn't it? We talk about all the tech advances since the Apollo era. I mean, computing power, materials, everything. So why haven't human boots touched down anywhere else since 1972? What's stopping us?
Yeah, it tells you just how hard deep space travel for humans really is. It's not just getting there. It's keeping people alive for months or years, the radiation shielding, getting them back. It's orders of magnitude harder than sending a robot. But these journeys, robotic or human, they rely on some incredible machines. What are the workhorses, the rockets and spacecraft that have gotten us even this far? And what's coming next? Well, you've got the icons, like the Saturn V for Apollo. Huge. Then SpaceX's Falcon 9 and Falcon Heavy, doing a lot of the lifting now. And NASA's got the SLS, the Space Launch System for the Artemis moon missions. Plus there's Starship, the SpaceX vehicle aiming for Mars eventually. Still under development, but wow.
Huge machines and the spacecraft they carry.
All right, the Apollo Command Module, that classic capsule. Now we have Orion, NASA's capsule for deep space, and Dragon and Starliner taking crews up to the ISS. And of course, the robotic legends, Voyager 1 and 2. Yeah. They're actually out of the solar system now in interstellar space.
Incredible feats of engineering.
Yeah.
And the propulsion. That's key.
Definitely. Mostly chemical rockets still, right?
Yeah.
They give you that massive initial push to beat Earth's gravity. Super powerful, fast.
But incredibly fuel hungry. Not very efficient for really long trips across the solar system, let alone to the stars. They just burn through propellant too fast.
So what else is there? What's more efficient?
Well, there's ion propulsion. That's been used very successfully on probes like Dawn and Deep Space One. It uses electricity to accelerate ions like xenon to really high speeds. It's very slow acceleration, but incredibly fuel efficient over the long haul. You can keep thrusting for months or years.
Ah, okay. Like a super efficient engine for the long cruise phase.
Exactly. And then there are even more, well, experimental ideas like solar sails, using the pressure of sunlight itself to push a large, thin sail, no propellant needed at all, just sunlight. Projects like Light Sail have been testing this. It's slow to start, but constant acceleration.
Wow. Okay, so the tech is evolving. But even with better propulsion, let's talk about the really big distances. Interstellar travel. If Venus is, say, 40 million kilometers away on average, what about the nearest stars?
Yeah, this is where the scale just becomes mind-boggling.
The closest star system to us, besides our sun, is Alpha Centauri. Within that, the very closest star is Proxima Centauri. It's a small, dim, red dwarf star, and it's 4.24 light years away.
4.24 light years.
And then you have the two brighter stars in that system, Alpha Centauri A and B. They're a bit further, about 4.37 light years. More sun-like stars, maybe with planets.
And it's crucial to remember what a light year is, right? It's not time, it's a distance. It's the distance light travels in a year, which is enormous. 4.24 light years is roughly 40 trillion kilometers. Trillion.
40 trillion kilometers.
Okay.
And we said the furthest humans have gone is the moon, less than 400,000 kilometers.
Exactly. The comparison is just...
Yeah. So reaching Proxima Centauri, I read Voyager 1, which is one of our fastest probes heading out, would take something like 70,000 years to get there.
That's the kind of timescale we're talking about with current or even near future propulsion. Tens of thousands of years, minimum. It puts the challenge into stark perspective, doesn't it?
It really does. So let's break that down. Why can't we reach the stars yet?
Right.
What are the biggest roadblocks based on what we know?
Well, the first is just that number we talked about. The sheer, almost incomprehensible distance, 40 trillion kilometers to just the nearest one.
Distance is number one.
Number two is speed. Our fastest spacecraft are still incredibly slow on an interstellar scale. We need breakthroughs to get anywhere near a reasonable fraction of light speed.
Okay, speed. What else?
Fuel and energy. Chemical rockets are out for interstellar. Ion drives are too slow for practical interstellar travel times. Solar sails get very weak far from the sun. We need fundamentally new propulsion concepts. Fusion rockets, maybe antimatter, laser-push sails, things that are currently science fiction or very early theory.
And even if we solve propulsion, what about the humans on board?
Huge problem. Radiation in interstellar space is intense, far worse than within our solar system's magnetic bubble. Shielding a crew for decades or centuries is a massive challenge. And then there's life support. How do you create a closed ecosystem that can sustain people for generations without any resupply? Food, water, air, psychological health.
Generations. Wow.
It raises this fundamental point. It's not just about building a faster engine. It's about building essentially a generational starship, a self-contained world. The cost, the time, the resources. It requires breakthroughs across physics, engineering, biology, everything.
So interstellar travel.
Yeah.
It's a dream for the distant future, maybe.
It seems that way based on current understanding, yes. A very long-term goal.
Okay, so maybe let's pivot back closer to home, because our deep dive found something really surprising within our solar system. Remember Venus, our closest neighbor on average?
The one with the hellish surface.
Exactly. Most people hear Venus and think acid rain, crushing pressure, lead-melting heat, and the surface is like that. Let's be clear, about 475 degrees Celsius, hotter than Mercury, atmospheric pressure 92 times, Earth's like being nearly a kilometer underwater, atmosphere mostly CO2, clouds of sulfuric acid, crazy winds, volcanic landscape, no water, living on the surface. Yeah, that's impossible with any tech we have now. Forget about it.
Completely hostile. Probes we've sent barely last minutes, maybe a couple of hours if they're heavily shielded Soviet Venera landers.
But, and this is where it gets really interesting, what if the key to Venus isn't the surface? What if it's somewhere else?
This is that creative shift in perspective we talked about, thinking outside the box, or rather, above the surface.
Right. Imagine this. You go up, way up, about 50 to 55 kilometers above that nightmare surface. There's a layer in Venus's atmosphere that is, well, surprisingly Earth-like. What are the conditions like up there?
It's actually quite remarkable. At that altitude, the temperature is around, say, 20 to 30 degrees Celsius. Comfortable room temperature, basically.
Have a nice day on Earth.
Pretty much. And the atmospheric pressure, it's about 1 Earth atmosphere, 1 atom.
So you wouldn't get crushed. You could like walk around outside.
Yeah.
Well, not walk, but float with just an oxygen mask.
In terms of pressure, yes. You'd need breathing apparatus because the air is CO2 and protection from the acid, but the pressure itself is fine. And the gravity, Venus's gravity is about 90% of Earth's. Very similar. Much better for long-term health than Mars's 38%.
Wow. Okay, so temperature, good. Pressure, good. Gravity, good. What else?
Solar energy. Venus is closer to the sun, so there's abundant solar power available up there, more than we get on Earth. And while there are winds, they seem to be relatively predictable at that altitude, potentially usable for maneuvering.
Okay, this sounds almost too good to be true. What's the catch? There has to be a catch.
The big catch is you're floating in clouds made of sulfuric acid droplets. So whatever habitat you have needs to be resistant to that corrosive environment. You're not on solid ground, you're in a very specific habitable layer of a toxic sky.
Right, so floating cities, like blimps or aerostats.
Exactly. That's the concept. Think large, buoyant structures, maybe filled with breathable air, which would naturally float in Venus's dense CO2 atmosphere. NASA actually studied this seriously with a concept called HAVOC, High Altitude Venus Operational Concept. It explored using airships for exploration and potentially, eventually, habitats.
HAVOC. Okay, so this isn't just like a wild sci-fi idea. People have crunched the numbers.
Oh, yes. It's based on known physics and atmospheric science. There are significant engineering challenges, of course, material science for the acid, life support, how to build and maintain these things, but the environment itself at that altitude offers compelling advantages.
So let's compare then. Why even think about floating cities in acid clouds when Mars has actual ground you can walk on? How does Venus's cloud level stack up against Mars's surface for long-term human presence?
That's a fascinating comparison. Let's look point by point. Temperature. Venus clouds, maybe 25 degrees average. Mars surface, average minus 60 degrees sequence. Huge difference.
Minus 60. Ouch. Okay, what about radiation? Mars has a thin atmosphere, right?
Very thin, so high radiation levels on the Martian surface, especially UV. You'd need significant shielding or to live underground. Venus's thick atmosphere, even at 50 kilometers, provides much better radiation protection, more comparable to Earth.
Okay, that's a big plus for Venus. Energy.
Venus, being closer to the sun, has abundant solar power. Mars is further out, sunlight is weaker, dust storms can cover solar panels. Energy is a bigger challenge on Mars.
And gravity, we mentioned that. 0.9 degrees on Venus in the clouds versus 0.38 degrees on Mars.
And that 0.38 G on Mars, we just don't know the long-term health effects. Bone density loss, muscle atrophy, it's a major concern for permanent settlement. Venus's gravity is almost perfect.
So Venus wins on temperature, radiation protection, energy, and gravity. Mars wins on having a surface.
Essentially, yes. Mars has solid ground, resources you can potentially mine directly from the surface, maybe subsurface water ice. Venus offers none of that at the habitable altitude. You'd have to somehow import everything or extract it from the atmosphere.
So the tech needed for Venus would be lightweight habitats that float and resist acid, advanced closed-loop life support filtering CO2, making oxygen, growing food hydroponically, solar panels that can handle acid, airships for getting around.
Precisely. Significant engineering, but potentially focused on leveraging the advantages of that unique atmospheric layer. It really makes you question what's more important for long-term human survival off Earth. Is it solid ground, even if the environment is harsh? Or is it more Earth-like conditions, even if you have to float?
Wow, okay. We have covered a lot of ground, or space, I guess. We went from realizing Venus is our closest neighbor to seeing how limited our actual human reach has been. Just the moon, really. Then we grappled with those mind-bending interstellar distances and why reaching the stars is so hard. And finally, the surprising twist, the idea of maybe finding a habitable niche, not on Mars's surface, but high in the clouds of Venus.
It really shows how dynamic our understanding is, doesn't it? Planetary science keeps evolving, and it forces us to reconsider what's possible, what's viable. The stars might be a distant dream, but the possibilities within our solar system may be in places we initially dismissed, like Venus's atmosphere. They could be much closer and offer unexpected benefit. The universe keeps surprising us.
So here's something for you to think about. As we keep pushing the boundaries, developing amazing tech for space, where does our future lie? Is it destined for that dusty, cold Martian surface, building outposts under a thin atmosphere? Or could our destiny actually be floating in those cloud cities above Venus, finding an almost Earth-like haven high above that inferno below? It's a wild thought. Maybe look up the HAVOC concept. It really makes you wonder.